All right, and I think we're live. I'm going to put us in gallery view so everybody can see faces. All right, I think we are live on YouTube. Wonderful. I think we got it right this time on the first try. Love when that happens. All right, welcome everyone. Welcome back to Astro Chats. I hope you're all having a great day. As a reminder, I'm your host and YouthAstroNet Community Coordinator, Erica Wright. We're excited to have you with us. In a moment, I'll be introducing our special guest. You can see on the screen here. As usual, she and I will chat for a minute before we kick things off, and then she's going to share some exciting research into galaxy collisions with us, which is pretty exciting. Some of you will remember that we touched on that on Friday, actually, in our tour of the universe with Dr. Pat. So hopefully we'll get to dive into even more of those questions that you had out there in the Twitter sphere and on our Zoom chat. If you'd like to join in on the conversation today, there's two ways for you to ask our expert questions as we talk today. You can either type questions in the chat box if you're joining us via Zoom. If you're joining us via YouTube, you can ask your questions on Twitter or Facebook using the hashtag AstroChat. So feel free to type those anytime throughout the session. We're gonna interrupt and ask a few questions as she's presenting to us, but also at the end, we'll have time for open-ended questions. And those can be all sorts of things that you might want to know about her research or maybe a little bit about her career. So without further ado, we have with us Dr. Kelly Blumenthal. Welcome, Kelly.
Hello, thank you. Thank you.
We're so excited to have you here with us.
It's so exciting to be called doctor.
I know that's still a little newer for you, isn't it?
It is pretty new.
Well, you've earned it. You work very hard.
I did, yeah.
So maybe we could start a little bit with what got you here to being Dr. Kelly Blumenthal, since I know you're a newly anointed doctor.
I am. I got my PhD in 2019, at the tail end of 2019. And I guess the biggest influence that got me into astronomy was my dad. And he really always loved astronomy when he was growing up many, many years ago. And always wanted to do it, but never could figure out how, and decided that, being a doctor and taking care of people was more important, which arguably it is. And that's actually what he's doing right now. So thoughts out to him and my mom, both are doctors in New York City.
Wow.
And they are doing their absolute best to keep everybody safe.
Well, thank them for all of us for doing that. We really appreciate it all the time, but especially right now.
Yeah, absolutely. And so like when I was a little kid, he would bring me out to go see whatever stars we could see in the night sky, living kind of sandwiched between two very large cities in Newark on one side and New York on the other side. So light pollution was a pretty big issue, but we could always see Orion in the winter. So I always knew where that was. And that was, I think, what I consider to be the only constellation for a very long time.
Wow.
And then I started to get into it a little bit more, and we started to go to like amateur astronomy conferences together, and it's always been something that we bond over together. So kind of our thing.
Fantastic. That's a really beautiful way of getting into astronomy. A lovely way to connect with your family.
Yeah, I think so.
Well, thanks for sharing that little story with us. I think it's really nice to hear how people come into astronomy, and there's so many different ways that people get excited and want to join part of this community. So it's nice to hear the different types of stories. So I know you brought with us today some really fun images and visualizations all about galaxy interactions, right?
I did indeed.
I'm very excited. So maybe we can start with you sharing your screen and showing us some of those things. Go through.
Absolutely. So, oh, right, yes. Let me do that first. I apologize in advance if this does not go like we want it to go.
That's okay. We've been talking about it's all a learning process for all of us. So that's what we've been talking about. And it's okay if things don't start out perfectly.
And let's press play. And does this look good to you?
That looks great to me.
Amazing. Okay. Well, thank you everyone for having me here. I really, really appreciate it. I hope I got the date right. Time is kind of nebulous right now. And so I'm going to talk to you guys today about the topic of my PhD thesis, which was galaxy interactions, galaxy mergers, as they're often called as well. And I love comparing this sequence of events to a tango. I just think it is the most descriptive way to understand what's actually happening throughout the course of an interaction of two or more galaxies. And so what I thought we'd start with, though, and maybe we'll take a step back and think to, I guess you said Friday, you had some talk about galaxies. Maybe a few days before that, you had some more talk of galaxies, and just kind of try to understand exactly what is a galaxy. And I know that I can't pool the audience here, but if I could see you all and I could interact with you, I would love to hear about your understandings of what galaxies actually are. And maybe I'll just imagine that we're doing that and then skip forward in time to looking actually at this image right here. And to some of you, something like this might be kind of familiar. And to others, maybe it's not, and that's perfectly fine too. But what we have here is actually an image from Australia, from I think kind of like the middle of Australia. This very interesting mound of rock at the foreground. And then in the background, the night sky, you can see this huge band of light and dark and knots of material. It almost looks like someone took a Jackson Pollock paintbrush and just splattered all across the night sky these different colors and hues. And of course, you couldn't see this with your own eyes. This was taken with a camera that was able to expose for a long period of time. So it took in a lot more light, and the pupil of the camera was much larger than your eye, almost certainly. And some of you might already know, some of you might not, that this is actually a band of the Milky Way that we're seeing in our night sky. We're seeing the spiral arm of the Milky Way here. And a really good question is, how do we know that that's what that is? Well, we can kind of imagine maybe stepping out of the plane of the Milky Way and looking at it top down. And of course, we can't send a little spaceship up to, many hundreds of light years, many millions of light years away from where we are right now to take a picture of the galaxy from the top down like we see it here. But this is an artist's rendition of what we think the galaxy actually looks like. We call these kinds of galaxies barred spiral galaxies. Barred because of, I don't know if you can see my cursor, but this bar structure in the center of the galaxy here with these spirals going around it, hence the bar spiral galaxy. And we think, we're pretty sure, we have a lot of evidence to show that the solar system where we are, Earth, and where we are within this galaxy is right around there. And so what we see in the night sky, that band of gas and dust and stars that we're seeing, that the stars being the light, the gas and the dust, well, the gas is kind of invisible to our eyes, but the dust kind of shows where along where along the gas might be, because stars are forming within that dust as these kind of like cradles and nurseries of star formation within the galaxy. And if we can imagine, we're seeing the inside of the galaxy because we're seeing the bar, we're seeing edge on the bar of gas and dust, these spiral arms within the galaxy. And still this really great question of, how do we know this? How do we know that galaxies, that our galaxy looks like this? And one of the best ways that we know that that's true is because we can look out and see other galaxies that are kind of similar to it. Now, this is the Andromeda galaxy, and Andromeda is a really wonderful case because it's so close by. It's our one of our nearest neighbors to the Milky Way, which is our home. And it's been so prevalent throughout a lot of certainly modern astronomy and astrophysics, but also really ancient historical astronomy and astrophysics. It's been studied for hundreds, if not thousands of years. And you also might be familiar with this galaxy especially if you are familiar with Mac screensavers. Or maybe we should flip it on its head to make it a little bit easier to compare. But Andromeda Galaxy is kind of part of our culture. It's part of what we know.
That one.
Yeah. Yeah, so something that's actually extremely interesting is that the Andromeda Galaxy and the Milky Way, our galaxy, are set on a collision course. And that's where this whole cosmic tango comes in.
Before we dive too deep into the collision course, how soon is that actually going to happen? I know that can sound scary to some of us.
Yes, that can sound very scary. You're absolutely right. And I probably should have said that nothing will happen to our planet. So this will happen in about 4 billion years is when the like nitty gritty stuff of the interaction is actually going to occur. But more than that, even if it happened tomorrow, we probably wouldn't notice other than what we would see in the night sky. Because the distance between stars in galaxies is so huge that two stars are not going to collide with one another. We're just gonna be like moved around probably within the mess of stars that occur when the interaction actually gets going.
Okay,
so don't fret, everything will
be
be
a lot
better. So let's see what this actual collision course looks like. And I should mention that I've added some annotations and some images to this video, but this video is not my own. It's a simulation from NASA and from their outreach team. And actually even the images are not my own. I scoured them from all over the internet. So if you're interested where those pictures come from, just let Erica know or let me know at the end. And I will be happy to give that to you.
One more thing before you hit play. You said the word simulation. Could you just kind of give us a quick tidbit of what that actually means?
Yes, absolutely. Thank you for asking that. I sometimes forget that people don't know. So we can look out into the night sky. I point the sky is that way for me. We look out into the night sky and we're able to observe things happening in the universe, but we can only really take snapshots. We're just taking pictures, basically. We don't actually know, we don't necessarily know what's happening throughout time. We're not taking a movie. And so when astronomers kind of piece together pictures in order to get a coherent understanding of what, or a continuous understanding of what galaxy mergers look like setting up these stages of galaxy mergers, if you've ever seen that before. It's almost like they're taking individual snippets of film from different movies and piecing them together to form something. So you might have a piece that's coming from Pulp Fiction, and a piece that's coming from La Vita è Bella, or a piece that's coming from footage of the Pope in 1950, and saying that those things all make a coherent story. And you might be able to create a coherent storyline and fabricate it, but you're not necessarily getting at that directly. So what simulations do, or rather what astronomers like myself and my thesis advisors and many, many, many others, what we do is we take everything that we understand about physics, about the physics of star formation, about where and how stars form, about everything we know about gravity, and so many other different things that you can add. You can almost add an infinite number of things. You can imagine maybe black hole physics and the how gas falls onto a black hole to create these incredible jets of material that come out of it, and how all of that kind of interacts with each other and creates maybe like a cycle of material that you might be able to imagine. So it's a very complicated process itself, but we think we know how those processes at least individually work, and we can put them into a computer, what we call a computer simulation, and effectively just hit go and then see what happens when we step through time and see how two galaxies might interact with one another, or even in the case of what's called cosmological simulations, you start at as close to the beginning of the universe as you possibly can, with all of the physics that we understand, and perhaps it's physics we don't understand, and we press play, and we can produce a universe that looks almost exactly like the one that we see today. And that's, if you're interested, that's the illustrious TNG simulations, and those were also part of my thesis, and it's really interesting stuff as well. So when I say simulations, all I mean is that we are using computers to try and get a better understanding for all of the intermediate steps that happen between two galaxies just seeing each other, to actually interacting with one another.
Okay,
and that's
great.
what we're going to see right here.
Great.
Sorry,
So
that was
you take,
very long-winded.
no, that was great. And that was really helpful. So you take all of the pieces that we understand, right, within astrophysics, and you put them into this computer model, right? Is that what you're saying? And then you play that out to see, kind of help discover those pieces that maybe we don't have pictures for right now.
Yes, absolutely.
Great. Awesome. I'm excited to see this.
Amazing. Let's go. All right. So we start with the Milky Way, our home. This is where we are. And we're now zooming out to look at what's called the local group. These are just galaxies that are kind of nearby. Andromeda is there, and we have another couple smaller galaxies that are also there. And this is what I said when I said galaxies see each other. These are two people who see each other from across the room, and they are getting ready to dance with each other. They have made eye contact and they're about to go. And so they make their initial pass by one another, and you see these huge arms of gas, and what you can't see it, but there's gas in there, there's dust, there's star formation happening. They pass again, and of course their dance becomes closer and closer as they get closer together, and as it progresses, and then finally ends in a final embrace with the final massive elliptical galaxy that forms when these two galaxies will come together in many billions of years. And so just as we could go from looking on Earth to seeing the Milky Way, to stepping out of the Milky Way to look down at the top view and then see all of this play out in what I called our local group, we can do the same thing but in reverse. And that's what we're gonna do in this next video that I wanna show you guys. And this is what this will look like. Ooh, no, don't start yet. This is what this will look like from our perspective, standing here on Earth. So this is a familiar image. I wanna say this is also, these are all simulated images. So these are computer generated images. This is not necessarily real, but this is a very good idea of what it probably will look like if we could see it, if we were around in 4 billion to 8 billion years. And so this is familiar. We have our band of the Milky Way coming up over the horizon, over these mountains, and you know, band of gas and dust and stars that we saw before. Maybe there's some knots of star formation you can imagine are happening within that band right there. And you can, so we have Andromeda that's also in this image. If you can find her, I challenge you to try and do so. She wouldn't look quite like this in our night sky, especially not if the Milky Way were so bright, because it's fairly faint. But at this point, Andromeda is about 2.5 million light years away from the Earth at this point. And if you want to know about light years, let's talk about it at the end of this video. So this is where we're starting. Again, Andromeda, 2.5 million light years away. It gets much closer and closer. You have this whole mess of material that's happening over this period of time. Eventually, it just really turns into a ball of stars that we see in our night sky. And maybe I'll just play that again because it's a little quick. Go back to the beginning, and of course we have Andromeda here. We see it get much closer here. Ooh, oh my goodness, wow. Yes, we see Andromeda get much closer. This is at about 4 billion years now is where this is. And then just after that point, everything is tidally disruptive. You have tidal tails and bridges and arms going every which way. And of course, finally, the star formation that we might have seen in the very beginning of this video, I'll show it again because it's very interesting to me.
It's beautiful.
So this is our first passage, and all of the star formation that's happening there, and again there, eventually tapers off as you get further and further through the merger that's going on. And then again, finally, our big ball of stars in our night sky.
So I have a quick question about that. Some of those images from the Earth's perspective were really beautiful, but I imagine just like in the first image, they're not actually what our eyes would see, right? They're what our telescopes would see. Is that correct?
Yes, they are what our telescopes would see. They are what our cameras would see. It might even be too large in the night sky for our telescopes to be able to focus on any like significant chunk of it. We would be able to look at parts of it, certainly. But it actually might even be better for amateur astronomers just to go out with their maybe small telescopes or small cameras and get a much wider field of view of what will be the entire night sky when this all happens.
But you would need something to gather light for a really long time, right? Our eyes wouldn't see quite the same beauty.
No, unfortunately not. Just like with all the other images that I've shown, you really need to have the light bucket collecting as much light as possible in order to see images like that. And the same thing with, of course, images like these. So these are all images of what we see in the night sky with Hubble. These are all Hubble images, Hubble Space Telescope. So that's actually not on Earth, that's in orbit around the Earth. And they're all looking at different instances within these two galaxies merging process. And just like I said before, we can kind of maybe construct like a storyline that's happening using just these individual pieces. But it really requires that we, in order to fully understand what we're actually looking at with sequences of galaxy interactions, we do need computer models because there's really just no other way. And with that, I will play you one of my simulations. Very dinky, but close to my heart nonetheless, and take your questions if there are any. It'll come back again.
Yeah, could you tell us a little bit about what's happening in your simulation?
Oh yeah, of course. So this was a very, very crude simulation. And I say crude because there were only really 3 things in it. There's dark matter, there's stars, and there's gas. And there's no star formation that's happening in these simulations. So all those knots of like pink that you might have seen in any of the images that I showed, that's regions where star formation is like really happening. All of that is not in these simulations. But what I was really interested in is looking at how gas moves around. So the individual points that you might be seeing, the individual particles here, these are all gas particles, and they're interacting with each other much as they would. So the initial, what's now showing here is this spiral pattern that's forming as a result of the gas just existing within this gravitational field. And those clumps of gas are gas that's being funneled into the center of the galaxy, into its nucleus. And what we were kind of thinking, what we're extrapolating from that is that the interaction itself creates these clumps of material where star formation might occur and probably would occur if there was any star formation within these simulations. And that those clumps actually migrate toward the center of the galaxy. And that is we were thinking that's a major driver of its evolution from a spiral galaxy into an elliptical galaxy.
That is so neat. So I'm going to remind people to ask their questions on Facebook and Twitter using the hashtag Astro Chat. I'm monitoring that while Kelly and I talk here. But I actually have a couple questions for you. One based on a question we actually got last week that I'm hoping maybe, since this is more of your expertise, you might be able to answer it. When we were briefly talking about galaxy interactions, a question came in about, so you mentioned, I guess I'll preface this, that nothing's really going to happen to our planet and our stars. They'll pass by things, but there's not going to be all these big collisions. But there was a mention that the black holes, what happens to those, and do they merge, and kind of what's that process to the black holes? Because we did learn that every galaxy has a black hole at the center last week. So kind of what happens to the two black holes? Where do those go?
What a great question.
Was that a great question?
I think that's about like 5,000 people's PhD theses, probably.
Wow.
And many more into the future. But what I think is the prevailing theory is that these will all, the supermassive black holes at the center of these two galaxies will eventually merge. And we really just don't know what happens when that happens. Because it's almost inevitable that it would happen because they're so incredibly massive and the gravitational force is so huge that they would have to merge with one another. But we don't necessarily know how that would affect the galaxies. There's a lot of people doing research on that, though, and I am definitely not an expert.
That's okay. I think that's a really great thing to point out, though, that there's, as you're teaching us now, there's a lot still unknown in astronomy. There's still a lot of really great, interesting questions, and that's not a bad thing. That's, part of why people go into the field, is that there's questions to still be answered.
Yeah, exactly. It's like a big puzzle, and we don't know what the pieces look like.
Makes it even harder. I love it. So another question that I kind of have, because you've used this term and a couple other people have used this term, and I think we'll probably hear it more throughout this month of Astro Chats, is use the word tidal. And when I hear the word tidal, I'm thinking of going to the beach and the tides coming in and going. And maybe you could kind of help us better understand what that means when we're talking astronomy.
Yes, absolutely. So honestly, it's kind of similar. What you're seeing when you get tides on the beach is the gravitational pull of the moon on the Earth pulling water in and out of the beach, in and out of the shoreline. And it's having this kind of global effect on us. But that pull is coming from a gravitational force, the gravitational force between the Earth and the moon. So we exert a gravitational pull on the moon, but it also exerts a gravitational pull on us. And when I say tidal, and when anyone who's talking about gravitational interactions like the ones that you might see in this really silly simulation or in any of the other simulations that I've shown you before, we're referring to what's occurring right now, these bridges of material between the two galaxies, or the kind of arm of material that, or the tail of material that's coming out on the other side. And those are referred to as tidal features because they form almost entirely from the gravitational interaction between the two galaxies. And so, yeah, tidal really just refers to gravity.
That's great. That makes it so much easier to remember and to understand when you think tidal, it's the same force, type of force causing our tides as it is out there. But in your instance, we're talking about the clouds of dust and gas versus here on Earth talking about perhaps the water in the ocean. That's wonderful. Thank you. And then another thing that you mentioned that's in here, and I know a lot of people, and I think we've got a few people set up this month to talk about it a little bit more in depth, but I'd love to peek into it just a little bit now, is in your simulation, you mentioned dark matter. And I think for a lot of us out here, that, and obviously even I know for astronomers, it's a big mystery. Could you just tell us a little bit about your understanding of dark matter, or what, what might be good for us to start to understand about dark matter? Because it is such a mysterious thing.
It really is, and it is still one of the biggest mysteries in astronomy and has been for several decades. But really, the way that we know that it has to be there is by looking at the way that stars and groups of stars move in galaxies, and by looking at the way that galaxies move in giant clusters of galaxies. Very similar concepts, but by looking at their motions, what we actually can figure out is that, well, at a certain point, within maybe the very core of the galaxy, stars tend to move in a very particular way. That's called solid body rotation. And then as you get farther and farther out from the core of the galaxy, if you're talking about a spiral galaxy, what we would naively think is that moving farther and farther away from the center, you will actually wind up decreasing your speed that you're going around the galaxy. So if you're fairly close by, maybe you're moving pretty fast, but as you get farther and farther away from the center, you're getting slower and slower and slower. That's what we would naively think. And that makes a lot of sense based on how we understand the motions of material, really just the motions of planets in our solar system, all of the moons around Jupiter, any of the satellites around the Earth. All of those pieces of evidence tell us that as we get farther and farther away from the object that we're orbiting, that we're going around, we get slower and slower and slower. And so an incredible woman by the name of Dr. Vera Rubin, who is near and dear to my heart, made a bunch of observations in the late 60s and the early 70s that showed that that's not the case. That when we get farther and farther out from the center of the galaxy, we're actually staying at basically the same speed. We're not getting slower, we're not getting faster, but we're staying almost exactly the same as we go out to really far distances. And what that says is that there has to be something else in the galaxy that we can't see, that we're not accounting for, that is affecting the motions of these objects within the galaxy. And we see the same thing at larger scales, at the scales of galaxies moving around in galaxy clusters. And so what this says then as well is that not only is it something that's within galaxies that we can't see, that we're not taking into account, but it's also something that's in the largest structures in our universe that we can't see, that we're not taking into account. So there are probably as many different theories for dark matter as there are people on this planet. But the prevailing theory is that it is, or the way that we treat it anyway, within simulations, within these kinds of simulations, and the way that most people typically think about it, is a particle that we can't see, that doesn't interact with what we know of the universe, our known universe, in a way that we maybe could have predicted. And really all that I mean by that is that we can't shine a light on it and see what it is. It doesn't interact with light in the same way that gas and stars and dust and regular, people do. Reacts in a very different way. And so actually another way that we know that some kind of dark material, dark matter has to be out there in the universe is by looking at these images of gravitational lensing. And that's one of the coolest things. I'm really sorry to say that I don't have any pictures to pull up right now, but what you often see when you look at giant clusters of galaxies is arcs of light that shouldn't be there. Because when we look at them and we observe that we observe maybe where they are with respect to us, so that's trying to get that's making a measurement of their redshift. It's really just how far away are these objects from us. They are significantly farther away than the galaxy cluster itself. And so what's actually happening is that the galaxy cluster, with all of its dark matter, is acting as a lens, much like my eyeglasses act as a lens to make the light focus in a different way into my brain so that I can see things clearly. The galaxy cluster is focusing light from the extremely early universe in such a way that it looks like little slivers of, almost like bananas of galaxies. They get stretched and like morphed around. And in looking at the shapes of those images and in looking at the distribution, where they are on the plane of the sky where the galaxy cluster is, we can actually figure out, we can backtrack where the dark matter has to be. And that gives us a much better understanding of where it is, maybe not what it is, but at least where, and the influence that it has on the universe that we can see.
That was really helpful. Thank you. I feel like I have a slightly better understanding of what it is in the sense of what astronomers currently understand, right? Since obviously we still don't know what it is. Yeah, there's some really neat, interesting things in astronomy that are still so unknown. I find that so exciting. Obviously, you do too. What you're looking at, right? How I've got kind of a question for our young people that are starting to think about school. Obviously, you told us how you got interested in astronomy, but how did you end up studying galaxy interactions? I think one thing a lot of young people don't know is like, how do you find this specialty? How did you choose that? Because there's so many interesting things in astronomy. How did you come along and say, galaxy collisions, that's what I'm going to focus on?
What a good question. I've actually never, I have like a vague memory of being like 12 and thinking I'm going to study theoretical galaxy evolution. not even really understanding what those words meant together, but I knew the words and I liked how that sounded. And that's, honestly what you're doing when you're studying galaxy collisions is how galaxies evolve in this very, very particular way.
I think that is probably, I don't know that I know any other 12-year-olds that have thought that.
I was an interesting child. I think I must have seen some pictures like these at some point in my childhood and thought, wow, those are so cool. I want to figure out why that's like that, which just kind of spurred me down a really wonderful rabbit hole that I'm still in to try and figure out why these pictures are so pretty.
That's wonderful. So it was kind of the aesthetic of astronomy that pulled you into the research that you did.
Yeah, I think so. At least in the beginning, and then it turned into a real love of trying to understand things in a really like fundamental way, and a love of math and coding. I discovered coding in grad school. I didn't know really what it was until then, and I love it. It's the coolest thing. You have so much control, and you can create so much that I like theoretical anything is just mind-blowing for me.
So I'm going to ask that we stop sharing the screen for a second so people can see our faces. And then I want to dive into that a little bit more because I think young people today are much more aware of coding than I think perhaps you and I were when we were their age. Although HTML was pretty cool when I was in middle school. Uh, for those young people out there, MySpace was a thing, and you could really personalize that area, your MySpace account with HTML. But obviously today, the coding that you're being introduced to is even more advanced, allows for more personalization. And so maybe you could talk a little bit about coding and kind of how you came to starting coding and just give us a little bit more insight into coding and what it means for you. And
Yeah, absolutely. So I think my high school had a computer science class, but I didn't really know what that meant, and I didn't really care. I should have cared. If I could go back, I would tell past me to care about computer science much more than you do. But when I went to college, so I went to Boston University. I'm sitting here right now in Cambridge, so it's right across the river from me. And I should say Cambridge, Massachusetts, because there are two. And in my undergrad, I took one class that introduced us to this ancient language called IDL, which I had never heard of. If you're not an astronomer, you've never heard of it. And even if you are an astronomer and you're fairly new to the game, you're probably like, what does that mean? And it was so, I hated it. It was, the thing that I really hated about IDL, so that means interactive data language, was that it would just seemingly break, and you would try to write something and tell it to do something, and then it, like, based on the conditions of your computer, it sometimes wouldn't do it. Just mind-boggling to me how that could possibly happen. And so I resisted for a very long time getting into Python and actually understanding the structure of code and creating things with code, because I had such a bad experience with this one particular language in one particular class that I had other reasons to not enjoy. But once I started getting into Python, the documentation for everything, so all of the like user manuals for all of the different packages that you might want to use, are so incredibly well written. And the community online of people who try certain things and they ask questions and they kind of workshop the answers on these online forums, I just found it so useful. And any question I have or had, or probably will have about coding in the future, I can probably find at least part of the answer to what I'm looking for online, and then I can piece together the rest with what I know of how the individual packages work, and then how they, and all the material that's available to me on the internet. And so it really just became this, again, like a puzzle, like you have pieces of a puzzle that you want to put together and you have to go in different places to find those pieces. And it is just a really enjoyable process for me to see how it all fits together. And when things do work, so when you test your code and you can actually see that it's doing exactly what you wanted it to do, it is one of the most rewarding experiences, the most rewarding feelings of actually doing science. And I know for a long time, people, I think especially those maybe who didn't grow up academically in a world where coding was so central to everything that we're doing, kind of resist thinking of coding as being a part of science, but it is an integral part. It is a central piece of what it means to be a scientist today. And I think if you have the ability, if you have the means to try and learn to code, probably in Python, because a lot of different fields use Python, it'll be so useful for you. I should also say, not only in the way that not only in your coding and your scientific practice and whatever you're trying to do with that, but also just in the way that you think, because coding requires that you have a very set list of steps that the computer needs to go through in order to solve the problem that you want it to solve. And if you don't write out those steps exactly, you're not going to get the right answer at the end. And so learning how to code effectively and efficiently really helped me, at least, understand how to think like that, and how to think like a computer. Think like a computer sounds really impersonal, but think really logically, and not get bogged down by all of the details that might not be totally relevant to what I'm doing in the moment.
And I think that's a really good point. It's a process, right? It's helping you to think through processes, which is critical in today's world. So I think that's a really key point to bring up, that it teaches you to think through process, because you're not going to get where you need to go unless you've got that process down.
Yeah, exactly.
I think that's a really great point. And I think that's a great point that coding is an incredible tool today that is useful across fields, and not just in STEM, right? It's not just in science and technology and engineering, but if you want to build an app that, I don't know what you want your app to do, to take someone somewhere, whatever, some new version of Twitch, whatever you want to do out there, you need to be able to code. So I think that's a really great thing to point out, that it's a useful skill in science and astronomy, but it is useful beyond this field. So
yeah, absolutely.
So we have time for maybe one more question, I think, before we call things off today. And one thing I think is important is for our young people to get to know scientists. I think a lot of young people, unless somebody in their family happens to be a scientist, don't know a lot of scientists out there. And so we've gotten to know you in your science, but I thought it might be nice for us to know something a little bit about you that maybe might surprise people, that they might not stereotypically think about as something that goes with science. So something about yourself that they might not know.
Well, there's a whole bunch of things. Maybe the most surprising to some people is that I majored in music in college.
I think a lot of people would find that surprising.
I was dual enrolled at Boston University in the College of Fine Arts and the College of Arts and Sciences. So at the same time that I was doing my astronomy and physics degree, I was getting a degree in music performance, in saxophone performance.
That is neat. That is really neat.
Yeah, and it's a really wonderful and beautiful thing that I haven't been able to do since I started my PhD, which is very sad to me. I have my saxophone downstairs in my living room, and it's collecting dust, very sadly.
That is very sad. Hopefully now that you're through your PhD, you might be able to find a minute here or there to start playing again a little bit.
Maybe I can, yeah, maybe if I can figure out a way to do that without totally annoying all of my neighbors and my roommates.
I think now's the time to start. People are really appreciating music from their neighbors more.
Yes, I'm sure they are. I think another thing that especially astronomers find surprising is that I am not actually technically in astronomy anymore, however you would like to define that. After finishing my PhD in August, I decided that I wanted to focus more on education. And so I'm currently doing a master's degree, so a 1-year master's at Harvard, at the Grad School of Education. And most astronomers who I tell that to are flabbergasted that I would abandon my PhD, but I really don't see it that way. I think I am building through this degree. I'm building on the skills that I learned as a pure scientist, and working toward something that I feel is more meaningful for me. And I think a lot of PhD students, particularly as they get toward the end, they get really bogged down in this idea that you have to follow a particular path, because that's the typical path being getting a postdoc, and then after that getting another postdoc, and then maybe if you're kind of unlucky getting a third or fourth or fifth postdoc, and then maybe if you're extremely lucky getting a faculty position. And that whole process didn't seem fun to me. And I find these kinds of things, science communication, science education, STEM education, much more worthwhile than sitting at my desk, interacting with no one.
Let me touch base on that, because although I think it is a stereotype and it can be very common in astronomy, this idea that you're kind of lone, a lone wolf off by yourself doing work. And I do know that you do spend a lot of time at your desk coding, as you talked about. But could you tell us just a little bit about what the interaction was? Because I think a lot of people are interested in science, but they don't think it meshes with maybe who they are as a social person.
Yeah, no, that's very true. And thank you for checking me on that. I think that it really does depend on who you're working with, and the group that you're in. So if you are a very social person and you want to have various kinds of interactions with collaborators or with your advisor, with other graduate students, it's 100% possible. You just need to look for it and you need to actively seek it. I know that there's a huge part of many different aspects of astronomy are very keen on these like huge collaborations where you're constantly on calls with other people, trying to figure out various problems. Maybe you're working with people all over the world, and that's something that I really love about astronomy, is that it connects people in a way that I really don't think anything else does. And not just people that are like within the same building, but people that are all over the globe. And it really encourages those kinds of interactions. I think that at least I get the sense that observational astronomy is a little bit more at the forefront of all of that, in terms of working collaboratively or effectively working collaboratively. But I do think that theoretical astronomers are really trying, or some are really trying to move forward in that, and move toward building active collaborations across the globe.
Great. So I think, maybe what you're saying is, as our young people come into astronomy, that there'll be even more opportunities for this field to be more collaborative and to be with other people and to engage in kind of that social aspect of the science, and that you won't necessarily have to be in a room by yourself,
Yes,
in that kind of
absolutely.
stereotypical view. So I think, it's good to be realistic about what the field is, but also that there are these opportunities. So thank you for that.
And I should say also that the field is really what you make of it. You have a lot of control over, especially if you stay in an academic track. If you stay after your PhD and you enter into a postdoc, it's I say especially because it's just a lot easier for you to have a significant effect on your institution or on astronomy in general, but that's not to say that undergraduates can't have the same kind of impact that a postdoc does. It just really depends on the timing and everything else that's going on. But I say that because if you see something happening that you don't think should be happening, for example, you have the power to do something about that. And that's true absolutely everywhere, but especially in astronomy, which is a really tight-knit community of people, of really wonderful people who most really just want everybody to get along and do right by others. But even just if you notice there's something lacking from the astronomy community that you're in, maybe it's in your undergraduate institution, or maybe if you go on to a master's or PhD, you realize that there aren't enough, like collaborative working spaces, or there's not enough interaction between certain groups of astronomers. You have the power to change that. And I really think that in astronomy in particular, people are very open to hearing those kinds of perspectives. Again, it does depend on exactly where you are, but I think it's becoming increasingly more true.
I think that is a really great point and a wonderful point to end on, is that the young people out there watching today have the power to change and to impact the fields that they're in and the places that they're in. And even our young middle schoolers that might be out there watching, that you don't have to wait till you're in college or grad school to start impacting the world around you, that you can do that now. You can join the astronomy field now. You don't have to wait till you're getting your undergraduate degree in physics to start joining the astronomy field. So I thank you for that kind of optimistic way of embracing this community. I think that's a really great way to end it, Kelly. Thank you.
Yeah.
And thank you so much for joining us today and having these conversations. I know I learned a lot. This is one of my favorite parts of getting to do this, is that I get to learn a new piece of science and astronomy every day. So hopefully our audience is learning along with me. So we really appreciate you being here with us and sharing your insights into the science, but also into the field and your experience getting your PhD and being part of the astronomical community. I think that's really key and valuable for all of us to hear about.
Yeah. Thank you so much for having me.
And thank you all out there for joining us today. Don't forget to join us again tomorrow. We'll be on at 11 a.m. Eastern tomorrow. Our special guest is going to be Dr. Griffin Hosenzada. He's an astrophysicist, and he's going to be teaching us how about explosions in space, something he's dubbing how to catch a supernova. I think it's going to be another very exciting presentation, and we'll learn all about another aspect of kind of these explosions and interactions in space. So don't forget to join us. The link will be posted on our Twitter, as we've been doing all along, or you can find the fall month's calendar at microobservatory.org. The whole calendar is listed there for you to see all of our special guests throughout the month. And so thank you one more time, Kelly, for being with us. We really appreciate it.
Yeah, thank you.
Have a great day, everyone. All right.